This is Lab 3 circuits. I'm Hudson Groover. So in Lab 3, we demonstrated principles of energy conservation, the loop rule, and current conservation, charge conservation, plus definition of steady state. And we used a voltmeter and ammeter to analyze circuits and examine behavior of capacitors. And the system was a circuit. I had to use a simulation because I'm studying abroad. So assumptions, it's a closed circuit, no heat loss, no interference, using simulations, so not real world data. Concepts and measurements, energy conservation, current conservation, and there are different measurements. So for the first circuit, we used two 1.5 volt batteries and two resistors of different resistance and looked at the current, which was 0.02 amps everywhere because of current conservation. And then when you disconnect one of the amperes and put a voltmeter, it's going to show 0 amps on the other ammeter because there is no current flowing because it is an open circuit, but it does show a voltage difference because of that. And then then measuring the voltage at different points in the closed circuit, we see that the voltages on, so each of the batteries is 1.5 volts, and then on the resistors is 0.96 and, well, negative 0.96 and negative 2.04, and this all adds up to 0 because of energy conservation. But in reality, there could be a voltage drop due to heat loss and resistance and other out-of-system effects. So here's the voltage where we see it goes up for the first battery and then again for the second battery, and then it's negative. So overall, it's a summation of 0 volts. And then if you put a parallel circuit with the 100 ohm resistor, the current can go around it, so it actually increases the current because there's less resistance to 0.06. And for another circuit, we use two different batteries with light bulbs, with one being 10 ohm resistance and one being 20 ohm resistance connected to a capacitor. So with the 10 ohm light bulb, when you connect the circuit, you see it goes bright and then quickly goes out. And when you discharge by connecting the wire without going through the batteries of the capacitor, it repeats the same behavior. And so the charge time is 1.6 seconds and the discharge time is also 1.5 seconds because it's hand time, so it's kind of hard to get it exactly. And then 20 ohm light bulb dulled and slowly goes out. In discharge, it repeats behavior, and those are the charge and discharge times. So some potential errors is it's a simulation, not real world, and charge and discharge was measured by hand. So what if you charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. And then use the ammeter to test it. I predicted the capacitor would charge much quicker. In the light bulb experimentation, we saw that the 20 ohm light bulb caused the capacitor to take longer to charge than when the 10 ohm light bulb was there. Essentially, I believe it should charge in nanoseconds at the speed of light for the electrons to reach the capacitor. In experimentation with the simulation, it seems to confirm this theory, but it also catches the batteries on fire. Interesting.